to carry on, let's take another example of an organic compound. This time we take acetylene. Acetylene has a formula of C2H2. Acetylene is the simplest alkyne present, where there is a carbon-carbon triple bond or a triple bond between the two carbon atoms. This is a possible structure for ethylene. So there is a carbon-carbon triple bond and a single bond between each carbon and each of these hydrogen atoms. Now, according to the valence shell electron pair model or VSEPR model, that triple bond is counted as a single effective electron pair. So there are therefore 2 electron pairs around each of these carbon atoms. Let's again go back to the electronic configuration of carbon. Carbon has an electronic configuration of 1s2, 2s2, 2p2. There are 4 valence electrons in this case, 2 core electrons. The valence electrons are the ones located in the outermost shell or the highest principal quantum level, the ones in shell number 2. These are the valence electrons, and it is again the valence electrons that are responsible for bonding. Let's try to distribute electrons of these valence, distribute these electrons or valence electrons in orbitals. So there are 3p orbitals. So this is 2p x, that's 2p y, and that's 2p z. And this is the 2s orbital. And in each of these orbitals, there is an unpaired electron. We have mentioned already that the carbon-carbon triple bond, just like multiple bonds according to the VSEPR model, they are counted as a single effective electron pair. Okay, so therefore, not all of these orbitals would be mixed in order to understand bonding in this case of acetylene, but rather only 1s and 1p. So 1s and 1p should give brand new orbitals or hybrid orbitals of what is to be expected to be an SB type. So the type of hybridization in this case would be SB, because it is formed as a result of mixing or hybridizing only 1s and only 1p orbital. So the hybridization type is SB. Only 1s and 1p orbitals are mixed, but the other 2py and 2pz orbitals were left unhybridized. So this is the 2py and that's the 2pz. And again, these unhybridized p orbitals were native. They are native actually. These are the native p orbitals, whereas these ones are the hybrid SB orbitals. And of course, there are 2 of them around each carbon, in this case of acetylene. Let's again draw a picture of orbitals in acetylene. So there are 2 SB orbitals around each carbon. Okay, so something like that. And from hydrogen, it is the 1s orbital that's responsible for bonding. And you can see the point of overlap between these orbitals. The point of overlap between the 1s and SB orbital from carbon, a point of overlap between this SB from carbon and the other SB from the other carbon, a point of overlap between that SB hybrid orbital from carbon and the 1s orbital from hydrogen. This kind of overlap is head-to-head or end-to-end overlap, which constitutes sigma bonds. So that's a sigma bond. This is a sigma bond, and that's a sigma bond. So there are 3 sigma bonds so far. Okay. Now, to get a representative picture of bonding, in this case of acetylene, we have to take obviously into account the unhybridized p orbitals, and there are 2 of them unhybridized on each carbon. So this is one of them. So that's like 2py on that carbon and 2py on the other carbon. Okay, so electrons located in these unhybridized orbitals get shared by the 2 carbon atoms, and this electron sharing is above the sigma bond and below it. So there is electron sharing above and below the sigma bond. And as you've seen before in the case of ethylene, this constitutes what's called a pi bond. So it's a pi bond. Okay, so far that we have talked about. Now, the 2pz, the orientation of the p orbital is along the z axis. Okay, so that something like that should represent the bz, okay, on that carbon, and this should be the bz from the other carbon. And again, these orbitals, or the electrons in these orbitals, also get shared by the two atoms. Okay, this electron sharing is also above and below the sigma bond. This also constitutes another pi bond. So therefore, there are two pi bonds which are formed, in this case of acetylene, between the two carbon atoms. The pi bonds are formed as a result of electron sharing of electrons in the unhybridized orbitals, or native p orbitals, from each of these carbon atoms. So therefore, in this carbon-carbon triple bond, there is one sigma bond, yes, and two pi bonds. So overall, there are 3 sigma bonds, in this case of acetylene, and 2 pi bonds. The molecular structure, or the geometrical structure around each carbon atom, in this case of acetylene, is linear. The bond angle is 180 degrees because the shape is linear. So to conclude, each carbon-carbon triple bond has 1 sigma and 2 pi bonds. So overall, in the case of acetylene, there are 3 sigma bonds, 2 pi bonds. The molecular structure is linear, the bond angle is 180 degrees, and the hybridization is SB.